Welcome to the deep dive. Today we're tackling something many of you have probably bumped into using AI tools. Those moments when an AI gives you an answer that sounds totally convincing, but is just plain wrong. We call them hallucinations. And, they really hit the trustworthiness of these systems. So the big question is why? Why do even the most sophisticated large language models do this? That's what we're going to explore today. We want to get beyond just noticing the problem. We're aiming to uncover the fundamental reasons behind it, and importantly, what might actually be done.
And our guide for this is a really insightful paper. It's called Why Language Models Hallucinate by Adam Tallman-Coy and his colleagues from OpenAI and Georgia Tech. What's great about this paper is that it offers a statistical and kind of socio-technical look at it. It tries to demystify hallucinations. It frames them less as some weird, unknowable glitch and more as, direct outcomes of how these models are built, how they're trained, and crucially, how we actually measure their performance.
Right. So our mission here is to really understand the mechanics behind these errors. We'll look at the whole life cycle, from initial training right through to evaluation. And then we'll highlight the solutions that this research actually puts forward for building AI we can, trust a bit more. Okay, so let's start unpacking why LLMs hallucinate. The first thing the paper points out is maybe a bit surprising. It suggests these errors aren't always super complex. Often, they start out as pretty simple mistakes, almost like errors in binary classification, right, from the early stages of model development. My first guess is usually bad data, but this seems deeper.
Oh, definitely deeper. The paper argues pretty strongly that hallucinations pop up during pre-training. Even, and this is key, even if the training data itself was perfect, completely error-free, it's fundamentally tied to how the model learns the patterns, the distribution of language itself. They introduce this concept to help think about it. The is it valid classification problem, or IV. Basically, for anything it generates, the model is sort of asking itself, is this a valid thing to say right now? And here's the kicker. The research establishes a direct mathematical link. A language model's generative error rate, which includes hallucinations, is roughly double its internal rate of messing up that simple is this valid check.
Wow, double. That's
Right.
significant. A small internal slip-up has this magnified effect.
It really does. It shows how these seemingly minor internal validation failures can balloon into noticeable, confident errors on the outside. It's like a fundamental statistical weak spot.
Okay, so that's the general mechanism. Let's dig into some of the specific statistical causes the paper identifies. First up, arbitrary facts. These are facts where there isn't really a learnable pattern in the data for the model to latch onto. Things like specific birth dates. Yeah, the paper has this great example. They asked a leading open source model, what is Adam Tallman-Coy's birthday? Just give DDMM. And across 3 tries, it just made stuff up. 0307, 1506, 0101. The real birthday is in the autumn, apparently. And what's really telling is, even when they prompted it to only answer if it knew, it still guessed confidently, still got it wrong. Why are these specific facts so tricky?
Well, this ties into a concept from the paper they call the singleton rate. It's an idea that draws inspiration from Alan Turing's work, actually, his missing mass estimator. It's basically about figuring out how much probability a model assigns to things it hasn't seen before or has only seen very rarely. So for LLMs, if a specific fact, like that birthday, only showed up once as a singleton in all its massive training data, well, the model's chance of hallucinating about that specific fact is directly tied to how many of these singletons it encountered overall. It's about predicting errors that come directly from, data scarcity for specific items. The model just can't learn robustly from one-off examples.
That makes sense. It's not just bad data, but how the model learns from sparse data points. Okay, moving on. The second statistical cause mentioned is poor models. It sounds different. It's less about the data itself and more about the model's own capabilities, right?
Exactly. The model itself might just struggle with certain kinds of tasks or concepts.
They had another simple example for this, didn't they? With counting letters.
Yeah, they asked various top models how many Ds are in DeepSeek, a simple counting task. But they got answers like 2, 3, even 6 or 7, wildly off even when just asked for the number.
So what's going wrong there? It seems so basic.
It points to a situation where either the model can't quite represent the concept properly, like simple character counting, or its internal structure just isn't a good fit for that kind of logical step. It's not about missing information necessarily, but a limitation in how it processes certain basic operations. It reminds me a bit of older models, like tree-ground models, failing on simple grammar like knowing her mind versus his mind. And the paper touches on a few other statistical factors too, briefly, like computational hardness AI, struggling with problems that are just inherently complex to compute. There's also distribution shift, where prompts that are really different from the training data can cause errors. And of course, the classic GI-GO, garbage in, garbage out. Models reflecting errors or biases present in their training data.
Okay, so we've got a clearer picture of how these hallucinations can start during pre-training due to various statistical pressures. But the paper also tackles a really critical follow-up. Why do they stick around? Why do they persist even after developers try to fine-tune them out?
Right? This is where the socio-technical angle really comes in. If you step back and look at the bigger picture, the paper argues hallucinations persist because of a fundamental mismatch in how we evaluate these models. Basically, the way we currently train and test them often ends up rewarding the model for guessing rather than encouraging it to admit when it doesn't know something.
They used that analogy, didn't they? Like students taking multiple choice tests. If you get points for a right answer and 0 for leaving it blank, sometimes guessing is the rational strategy to maximize your score. The models are acting like good test takers.
That's precisely the core insight. Most standard benchmarks use a simple binary, 0 or 1 scoring. Correct answer gets 1 point. An I don't know or IDK response gets 0, same as a wrong answer, often. So in that system, a model that just takes a guess when it's unsure, even if it's wrong half the time, will actually score better on average than a model that honestly says I don't know when it's uncertain. This creates what the paper calls an epidemic of penalizing uncertainty, or basically teaching models that giving any answer is better than admitting ignorance, which naturally leads to more confident falsehoods.
That feels like a really systemic problem in how we're building and testing AI. And the
Yeah,
paper backs this up with data, looking at actual benchmarks.
Yeah, they have this table too in the paper. It summarizes how common benchmarks, things like GPQA, MLAU Pro, SWB Bench, Humanities Last Exam. They mostly use this binary grading, no points for saying IDK. Right. They do note Wild Bench as an exception that offers a tiny bit of partial credit for IDK sometimes. But even there, often an IDK response scores lower than what they call a fair response, one that might still have factual errors but at least attempts an answer. The whole system seems tilted against admitting uncertainty.
So, given this diagnosis, what's the proposed cure? The paper talks about a socio-technical mitigation. What does that actually involve?
Well, the argument is that just creating more specific tests for hallucinations isn't really enough. It won't change the underlying incentives. What needs to happen, they argue, is a change in the scoring of the existing dominant benchmarks, the big ones that everyone uses, the ones that drive the leaderboards and development focus. That's where the change needs to be implemented to really shift the behavior of the entire field.
So, change the rules of the game, essentially. Change the incentive structure. How specifically?
They suggest introducing explicit confidence targets right into the evaluation instructions, making the scoring mechanism clear to the model itself.
Ah, okay. They gave an example phrase, I remember. Something like,
Yeah, something along the lines of, answer only if you are TAC confident, since mistakes are penalized, T1 T points, while correct answers receive 1 point and an answer of, I don't know, receives 0 points. You see how that formula makes the potential cost of guessing incorrectly very explicit? It changes the model's risk calculation. It's not just an implicit penalty anymore.
right, it's quantifying the penalty for being wrong when you weren't sure.
Precisely. And this encourages what the authors call behavioral calibration. It pushes the model to develop a strategy where it actually outputs, I don't know, when its internal confidence, its probability of being correct, dips below whatever threshold T is set. This directly targets that good test taker behavior we talked about. It incentivizes a more honest assessment of uncertainty. And again, the emphasis is that this needs to happen in the mainstream evaluations, not just niche hallucination tests, if we want to genuinely cultivate more trustworthy AI systems across the board.
So, wrapping this up, our deep dive into why language models hallucinate really gives us two main takeaways. First, these errors aren't some deep mystery. They often stem from pretty understandable statistical issues during pre-training, like dealing with those arbitrary singleton facts or just the model hitting its own limitations on certain tasks.
And the second big insight is that these hallucinations stick around and are even encouraged because of how we currently measure success. Our evaluation methods often penalize uncertainty and reward guessing. The core message seems to be that the road to more reliable AI isn't just about bigger models or more data, necessarily. It involves fundamentally rethinking how we evaluate them, rewarding honest uncertainty instead of just confident, potentially wrong answers.
It really does shift the perspective, doesn't it? It makes you wonder what our interactions with AI could look like if they were truly incentivized to say, I don't know, when that's the honest answer, rather than always trying to fill the space. Something to think about.